Hello everybody, welcome to first session of this course. As you can see here, we have a schematic that we are going to design throughout this course. I divided to some sections so it will be more clear and more easy to understand. Let's check it and see what we have in this schematic. This first section is our power section. In here we have a DC jack that can connect it to an external power supply. Also we have a 2-pin terminal here that can connect to an on or off switch, so you can turn on or off your board with this switch. To protect our board from wrong polarity connection, we used a Schottky diode here, as you can see here. When the user connects power supply to board in wrong direction, this diode will be short circuit and the current will go back from here in this direction and your board will not damage. As you can see here, for example, if user mistakenly put positive of power supply here and negative here, this diode will be turned on and will be short circuit, so the current will be flow from here to here and will be go back to your power supply, so your power section and your board will be safe. Our board power voltage will be 12 volt and we will convert it to our required voltage. For this purpose we used two types of regulator. First type is a DC to DC switching converter. The second one, as you can see here, is a linear 5 volt fixed voltage regulator. We used two types of converters because of some reason. A DC to DC converter for our GSM module and this 5 volt linear voltage regulator for other parts of our board, like MCU, like our MCU and those sections that are sensitive to power supply noise. The first reason that we use DC to DC converter for our GSM module is that this module power supply voltage range is from 3.4 volt to 4.4 volt. So there isn't any standard fixed voltage regulator for this range in market. There is 5 volt, 3.3 volt, 1.8 volt and 1.2 volt regulators, but they are not suitable for this range. Therefore, we should use adjustable version of linear regulators, or like this, DC to DC converters. Another reason is that our GSM module SIM800C will draw huge current when it's going to connect to network. It's about 2 amp. It's very huge. It's very big. There isn't any 5 volt linear regulator that can handle this current, okay? Therefore, we should use DC to DC converters because they can handle, in some cases, up to continuous 3 amp. And another reason that we use DC to DC converter instead of linear regulators is the fact of efficiency. Okay. If we use linear voltage regulator like this, EMS 1117, it's part number of this regulator. The output is 5 volt, right? The input voltage is 12 and our output voltage is 5 volt. And the current that will draw from this regulator is 2 amp. So the power that is equal to current times voltage will be equal to 10 watt, right? But our power supply voltage here is 12 volt. So this current, 2 amp current, will cross from here and drawn from our power supply. So the output power is 10 watt. The current is 2 amp. This current is equal to this current. So the voltage is 12 volt times 2 amp. So the power that will be consumed from our power supply is 12 times 2 amp, and it will be 24 watts, right? Okay. This difference in power will convert to heat. It should be converted and it should be wasted. And produce a lot of heat in this component. And this component will be very hot and will damage over time. But in DC to DC converter, voltage, the procedure is different, okay? In DC to DC converters, voltage and current both will change. In some cases, they have efficiency of 90% or even more. The procedure is like that. If you assume that the efficiency of our DC to DC converter is 100%, so our voltage is 4 volts, right? And the current is 2 amp. So our output power is 2 times 4 volts and will be equal to 8 watt, right? But because of its efficiency, it will convert power with efficiency of 100%. So here is 8 watt and we have 8 watt here too. Our supply voltage is 12 volt, so the current will be not 2 amp in here. It's 2 amp in here, but because of DC to DC function, this current will be not 2 amp. It will be 8 watt divided by 12 volt. It's going to be about 0.6 amp. So the current that will be drawn from our power supply is more lower. In this case, we don't have any power dissipation in here, so the component is not going to be very hot and will not damage over time. Another reason that we use two types of regulator is noise. DC to DC converters, switching converters, produce some high frequency noise on their output, okay, because of their switching function. This frequency can be in range of 20 kilohertz to even 500 kilohertz. Therefore, it can produce some high frequency noise on our power rays that is very harmful to sensitive part of our circuits. This switching frequency can be in range of 20 kilohertz to even 500 kilohertz. Therefore, it can produce some high frequency noise on our power rays that is very harmful to sensitive parts of our board, like MCU, and cause reset in our MCU or wrong operation in our sensitive digital sections, and our board will not work properly. In other hand, linear regulators have better functionality compared with switching regulators, better functionality in noise, producing noise on power supplies. So because of these reasons, we use two types of regulators in our board. One for our GSM module and its parts like indicators, and one for our MCU and sensitive parts like EEPROM or another digital sensitive circuits like date and time IC, sensors, or our LCD. And in here we also have an indicator LED. It indicates that our board is on or off when the power supply is plugged in, and our switch here on or off switch is on. If the power section is correct and there is no problem, this LED will be on, and we realize that everything in here is okay and our board is on. In next section in here, we have some decoupling caps like 10 picofarad and 22 microfarad and 100 microfarad capacitors, 33 picofarad also here. These capacitors is for decoupling and bypassing the noise that is produced by this switching converter. It doesn't let this high frequency noise to go to our GSM module. It can decouple it and don't let it go to our GSM module. Also, we have a large value capacitor in here. It's 100 microfarad to provide the current that is drawn by our GSM module locally, and also keeps voltage rail constant, okay, and doesn't let power rail to drop too much because of huge current that is drawn by our GSM module. Okay, in next section is the reset circuit. For GSM module, we use transistor circuit to control our GSM module from our MCU, as you can see here. I will tell you how to design this circuit in next sessions. Also, we have push button here to reset and on or off our GSM module manually. From here we can push this button down and our GSM module will be on or off. And also we can on or off our module by this pin in our MCU, this circuit in our MCU. Next section is our indicator LEDs. We have 3 indicator LEDs in this board, and all these 3 indicators is for our GSM module. We can monitor our GSM module status. This one is for GSM module status. It will be on when the module is on, and it will be off when the module is off. The next one is network status LED, when we can realize that our GSM module is connected to network or not by this LED. And the next one is for ring indicator pin of GSM module. We can realize that is there any call or message for our GSM module from this LED. We use this circuit to we use this circuit to inverse the logic of this pin, because it will be high by default and will be low when there is a call or message. So if we didn't do this LED would be always on. So we inverse its logic, so when the RI pin is high, our LED will be off, and when it is low, our LED will be on. We used this transistor circuits because that our GSM module I/O pin current is very low. It can provide very low current for its pins like this. It can only provide 4 milliamp per its I/O pins, so we use transistor circuit to buffer this current, so we have more current, and it's better to this for you, all of your circuits, and don't draw a lot of current from your IC, because it will be damaged over time. So when you provide these circuits for your IC, it will be work more and more in time. So in here you see our GSM module SIM card holder. It has 6 pins, one for data, one for programming power supply when you provide this voltage. You can program this SIM card. We don't use it in our board because we don't want to program this SIM card. One GND pin, one for clock, data clock, and one for reset, and one for its power pin. As you can see, there are some 51 ohm resistor. We call them termination resistor. I will tell you about them in next sessions. What is their usage? There are also some decoupling caps. In here you can see it is used for decoupling noise in these tracks. So we use them to decouple and don't let noise, our environment's noise, to damage our data. Its value is determined in datasheet. Its maximum value is determined in GSM module datasheet, and we will see this value in next sessions. Next is external EEPROM. In some situations you need to store your variables in somewhere that will be not erased when the power supply is off. So you need to store them in some places and use them later. Some variables like user password or some date or some time that you want to store in some places and use them in another time. As you know, our MCU 80 228 has internal EEPROM too, but in some times it's not enough for your application, so you have to use an external EEPROM to store your data. It's connected to our MCU on I2C interface. I2C use 2 pins for communication, one for data that's called SDA, and one for clock that's called SCL. You can connect up to 120 devices to this bus, and you can control and communicate with all of them in just 2 pins. It's awesome. As I2C is an open collector bus, I will teach you what is open collector in next sessions. So we need to pull up these lines with resistor. The value of these resistors can be in range of 2 kilo ohm to 10 kilo ohm, depends on our power supply. We use 4.3 7 kilo resistors in here. Next is time and date IC. It can store and update date and time even when the board is off, and you can read updated day and time by your MCU over I2C bus. It has 3-volt backup battery and crystal oscillator in here. It can connect to I2C bus by SCL and SDA pin without needing pull-up resistor. You placed pull-up resistor in here, so you don't need to use it here again, because they are on same bus. You don't need to use another pull-up resistor in here. Next is 8x8 keypad. As you can see here, it has 8 pins, 4 of them for its rows and 4 of them is for its columns. We also use this circuit to produce interrupt when any buttons of keypad is pushed down. It's a very simple and useful circuit. It just has 4 diodes and just 1 pull-up resistor. So if someone pushed any buttons of this keypad, it will be produce an interrupt and will tell your MCU that some buttons is pushed down. Next section is temperature and humidity sensor, DHT22. According to its datasheet, its power supply voltage is 3.3 volt to 6 volt DC, so we can connect to our 5 volt power supply. Its operating range for humidity is from 0 to 100%, and for temperature is minus 40 to 80 Celsius. Its accuracy for humidity is plus and minus 2%, maximum plus or minus 5%, and for temperature is its tolerance is lower than plus or minus 0.5 Celsius. It has 4 pins, one for VCC and one for GND. Its output is digital signal. It's not analog, and it communicates on just 1 pin over single wire interface. And because it's an open collector interface, we should use a pull-up resistor, as you can see here. To work this interface properly, we should use this pull-up resistor in here. Next section is 1.3 inch OLED display, as you can see here. This display just needs 2 wire for operating. You can use I2C interface for drive this LCD. It's awesome because you can use EEPROM, date and time IC, and this OLED display just by 2 pins, and it's very useful. In next section we have 3 relays. as you can see here. These relays can be used to switch on or off, or DC or AC loads. Also, we have a 12-volt output relay that can be used for 12-volt loads, like a 12-volt fan, or control another external relay, as you can see here. For controlling these relays, we need 12-volt source, so we use a transistor circuit to control these relays. Also, we have here freewheeling diode for protecting our MCU pins from damaging. I will discuss about it later. I'll tell you how it works. Also, we have these indicators LEDs, one LED per each relay. That indicates our relay is on or off. We use transistor for buffering current, because both relay controller transistor and LEDs are connected to same pins, and MCU pin just can source only 20 milliamp at 5-volt supply per GPIO pin. In next session, I will tell you how to design this transistor circuit and how to choose proper transistor and right value for these resistors to use transistor as a controlling switch. In here is our GSM module. This module has 42 pins, and as you can see, we use just some specific pins. We communicate with this module over serial UART interface. It supports 2 serial ports. As you can see here, one is here and another one is here. It supports 2 serial ports. One of them is full modem, you can see here, and can connect to devices that have full modem serial port. We use just RxD and TXD pins for asynchronous serial communication. Here we use 2 resistors as voltage divider. SIM800C maximum I/O voltage level is 2.8 volts, and voltages over 2.8 volt will damage its pins over time. And because our MCU I/O output voltage is 5 volts, so we need to decrease this voltage to proper value. Because of that, we used this voltage divider in here to decrease our MCU voltage. The PWR key, power key in here, is used to turn on or off module. Therefore, its circuit is here, you can see. Therefore, we connected it to a push button in here, and also connected to a transistor to be controlled by our MCU. RI pin used for ring indicator when SMS is received. When a SMS is received or someone is calling our number, this pin will go to low. At default, it's high, so we need we need this transistor circuit to inverse its logic. Now when there is no message or call, LBD will be off, and if there is a message or call, the LED will be on. So in here, SIM VDD, data clock RST, and DET is used for connecting to SIM card. As you can see, this pin is connected to SIM card pins, and VRTC pin in here is for connecting to backup battery. You can use a large capacitor or a rechargeable battery in here for its RTC, real-time clock. It has real-time clock in itself, and this pin is used to connect to external backup battery, or you can use a large capacitor in here to provide its power when the power supply is not connected. In here, net light pin indicates that our module is connected to network or not, and this status pin indicates module is on or off. The next pin are RF in here is for connecting to GSM antenna, and BT/ANT pin for connecting to Bluetooth antenna. These two pins are very important because they are high frequency signals, and also they are very sensitive. So in PCB layout, you should carefully route their tracks, okay? The tracks which should be calculated for impedance matching, and to have best performance. I will tell you next session what is impedance matching and why we use them. And to have best performance, you should consider some special situations, and we should set some rules for routing these kinds of tracks in our PCB layout. And finally, here we have our MCU. We use 80 MHz 328p microcontroller as our MCU. We use MISO, MOSI, SCK, reset, and GND pins, as you can see here, to program our microcontroller and bear Arduino bootloader to it. After that, you can use it just like your Arduino board and write your programs in Arduino IDE. Thank you very much for watching this session.